In this video, talk about spanning trees of a graph, and we'll look at some examples as well as a few different ways that you can construct a spanning tree of a graph. All right, so a spanning tree is just a spanning subgraph of a graph G that is a tree, and that's all there is to that. So the real problem here is how can we take a graph and produce a spanning tree of it? Well, there's several ways to do this. We'll look at this graph for an example, and I'll just give you three ways here that we can take a graph and produce a subgraph of it that is spanning and a tree. So here we'll start with the first way. And what we'll start with is just the vertex set of the original graph. So that graph up there, I've placed its vertices here. And what we'll do is we'll add edges from the original graph that do not produce a cycle. So we'll just keep adding edges, and then if the addition of an edge would produce a cycle, we won't add that. And so what will happen is we'll end up adding exactly n minus 1 edges because we know that the size of a tree is exactly n minus 1. Okay, so let's see how this works. So here I have the graph to the right, and I'll just pick an edge at random and add it. Right now I don't have any edges, so there's no way to produce a cycle. So I'll just add an edge. How about TV? And then I'll add, I don't know, maybe UV, and maybe TW. I'll add that one. Now notice I can't add UT anymore. That would produce a cycle. And I can't add VW. That would produce a cycle. So I'm just going to keep adding edges, knowing that I can't add UT and I can't add VW. So maybe I add UX. And again, I'm just adding edges from the original edge set. UX. Notice if I added XW now, that would produce a cycle, so I can't add that one. So maybe I add YW, and then maybe ZW. And now if I'm looking at the edge set of the graph over here, I can't add any more edges from there without producing a cycle. And indeed, I can see that the number of edges I have in this graph is 1, 2, 3, 4, 5, 6, which is one less than the number of vertices. And so certainly adding any other edge would produce a cycle. So this is one way to find a spanning tree, is just by adding edges. Another way to do this is to start with the graph already drawn. So there's the graph up there again. I've copied it down here. And what we'll do this time is, instead of thinking additively, we'll think subtractively. We're going to remove edges from each cycle. So I'm going to look at all the cycles. I'm going to pick an edge that lies on a cycle and remove that. And since I'm just removing an edge from a cycle, there's no possible way I could disconnect the graph. There'll still be a path between any two vertices if I delete an edge on a cycle. And so it should be good. So let's just pick a cycle here. I see this UVWT cycle. And so I'll delete a edge from that cycle. How about I delete TW? Okay, well, I still have a cycle here, UTV. So maybe I delete the edge UT. Let's get that one out of there. And then I still have, let's see, 1, 2, 3 more cycles in this graph. So maybe I select, I don't know, how about, so for instance, I have the cycle UXWV, back to U. So maybe I delete UV. That leaves me with this graph. I still have some cycles. For instance, UYWX and back to U. So maybe I delete this WWX. And right, so yeah, you should, like I'm saying, maybe I'll delete this one or maybe I'll delete that one. There's many choices in this process. So this is not always, right, this isn't a strict algorithm that's going to produce a unique graph. This is just one way of producing a spanning tree. You might end up with different graphs by doing the same process, just making different choices along the way. All right, so let's see, where else do I have a cycle? Well, I have U, Z, W, Y back to U. So I need to delete an edge from that. I could delete, say, ZW. Why not? Let's delete that one. And now I'm going to check again for cycles. I don't see any cycles left in the graph, and indeed I can see there are 6 edges in this vertex set of order 8, and so I have a tree. So notice how many edges I had to delete there. We started with 11 edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And I had to delete 4 edges to get rid of this. So here M, my original graph, was 11. My N was 8 vertices in this graph. And I ended up with a graph of size 7, which necessarily was a tree. So size 7. So this number, in general, if G has order n and size m, then we'll delete then the number n minus, so we need to end up with a graph of size n minus 1. So I need to delete m minus n minus 1 edges. I had to delete that many edges. This number, m minus n minus 1, is called the cycle rank of G, which is the minimum number of edges you need to remove in order to be left with a spanning tree of the graph. If we have a graph of size, so suppose G has size m equal to n, so same number of vertices as edges, then the cycle rank of G is m minus n minus 1, and so this would be just 1. These are called unicyclic graphs because they have one cycle. So for instance, a cycle itself is unicyclic, right? If I take here C6, my favorite cycle to draw, this is unicyclic. But we can also have other things going on with this graph and still just have a cycle of length, just one cycle in it. Connect that one. Maybe I have some things coming off of here. By the way, this is called a corona of a graph. This is still a unicyclic, or maybe I have something like what I want to draw here, a triangle with maybe a path or something coming off of it. This is also a unicyclic graph. And each of these has size equal to its order. Hence, its cycle rank will be exactly 1. Right? We'll only need to remove one edge from a cycle in order to obtain a spanning subgraph. So that's one way, is to think about edge deletions to produce a spanning subgraph. There's one more way I'll share with you, and we'll actually, the result of this is going to be a special kind of spanning subgraph that we're going to use to prove a result in the next video. So this third way is a little bit more involved than the other ways. The idea is to just pick a vertex of the graph, say its eccentricity is, I don't know, k, eccentricity v equal to k. And then for each I between 1 and k, I'm going to build this set A sub I. So let's start by just taking this graph and producing these sets. So I'm going to choose U as my special vertex. And then I'm going to let A sub 1 be all of the vertices that are distance 1 from that special vertex. So A sub 1, all the vertices of distance 1, that's T, V, X, Y, and Z are all distance 1. And then A sub 2 will be all my vertices of distance 2. So that would just be W. So the way eccentricity works is in each one of these sets A sub I, so given a vertex W in A sub I, it has to be adjacent to at least one other vertex in A sub I minus 1. Otherwise, the eccentricity wouldn't be what we claim it to be. And so what we'll do is we'll just pick exactly one of those vertices and let it be adjacent to my vertex W in A sub I. So that's the idea. Let me start by, right, A sub 0. Oh, that's a good question. Yeah, A sub 0 is just the vertex itself. So I should have made a note of that. A sub 0 is just U. So so each member of A sub 1 is adjacent to U because they're all distance 1. And so I start, here's U, and here's T, V, X, Y, and Z. And they have to be, I'll make each one of these adjacent to 1 in A sub 0. I only have one option. I have U here. And so I need to make all of these adjacent to U. And then I still have this A sub 2 set to deal with. That's W. And W, if we look back at the original graph, is adjacent to at least one vertex in A sub 1. In fact, in this case, it's adjacent to all of them. But in any case, it's adjacent to at least one. And so I'll pick exactly one vertex from A sub 1 to join to W. So what if I say pick V? So there, notice I have a choice and what I can let W be adjacent to. And I obtain this spanning tree. Now this spanning tree has a special property. We say that this is distance preserving. From U, distance preserving from U, because the distance from U to X, I don't want to use X, the distance from U to any other vertex V, I don't want to use V either, T, V, X, Y, Z, W, I don't know, distance from U to another vertex A in the tree, so this is my tree, is exactly the same as the distance in the graph from U to any other vertex A, for all A in vertex set of T or G. So it preserves all of the distances from U, and this is a helpful tool in some theorems. So in the next video, I'll walk through a proof of theorem 3.24, which gives us an upper bound on the radius of a graph in terms of the order of the graph. And we'll use distance preserving spanning trees in order to do that. I also want to keep in mind that what's our goal here with spanning trees is what we'd like to do is count how many, we've looked at one graph and we've seen there are many different spanning trees of this one graph that we could have, right? Each one of these is different from the other ones in terms of distinct labelings. And so one thing we can do just similar to what we had just done with Cayley's tree formula, is figure out how many spanning trees, labeled spanning trees, of a graph exist. We'll use some linear algebra to determine that. All right, see you there.